Jai Hind everyone. This is Naresh Kumar from Ajay Kumar Garg Engineering College, Ghaziabad. Welcome to another class of Optical Communication. Under Unit 2, in this lecture, we will discuss introduction to the topic dispersion along with its types. So today's topic will be dispersion and its types. So first of all, introduction to the term dispersion. Basically, in the second unit, we are discussing what happens when the light is propagating inside the optical fiber cable channel. So basically, in the optical fiber cable, when light propagates, generally two type of mechanisms that occur. First type of mechanism that is occurring inside the optical fiber cable are responsible for attenuation or losses. Whereas there is another type of mechanism inside the optical fiber cable which are responsible for distortion. So in the attenuation, there is reduction in the strength of or power of the signal. Whereas in the distortion, there is change in the shape of the pulse or light signal. So dispersion is basically a kind of distortion mechanism, or we can say that example of the distortion mechanism in the optical fiber is dispersion. So dispersion is basically nothing but it is broadening or spreading of light pulse inside the optical fiber cable. When the light propagates inside the optical fiber cable, maybe in the form of, let's say, pulses, so the pulses gets broadened or spreaded. So the broadening or spreading of light pulse is known as dispersion. So dispersion is nothing but it is spreading of light pulse. Spreading of light pulse. So whenever the light propagates through the fiber in the form of pulses, the pulses get spreaded or broadened along the length of the fiber, and this broadened is measured in terms of time. So basically, it is the broadening or spreading of light pulse along the length of the fiber and measured in the unit of time per unit length. So along the is a function of length. Here we can see that one example. Here the digital signal is being transmitted in the form of pulses. The pulses are 1, 0, 1, 1. So we can see that along the length as the length of the fiber is covered in the fiber. So in the first case we have the at a distance L1. When L1 distance is covered, we can see that there is broadening or spreading of light pulse. So due to which the two pulses mix with each other. So after spreading, the pulse get overlapped with each other. However, in this case, when the distance is less, these pulses are distinguishable pulses. However, when further more distance is covered, let's say L2 distance is covered, whereas this L2 is greater than L1. So whenever more and more distance is covered, the broadening or spreading of light pulse is further increased. And here we can see that the two pulses overlap with each other and result into indistinguishable pulses. Moreover, after spreading or dispersion, the two pulses may cross the level 0 or level 1. So it will be difficult for the receiver to identify whether 0 was transmitted or 1 was transmitted. That is, 1 may convert it into 0 or 0 may be converted into 10. Or we can say that this will result into error. Okay. So from this discussion, we can see that the broadening or spreading of light pulse is known as the dispersion, and dispersion can result into indistinguishable pulses, can result into errors, and this can also result into inter-symbol interference. Moreover, along the length of the fiber, as the length or distance covered increases, the bandwidth availability because of spreading of light pulse bandwidth availability also gets reduced. So the dispersion causes the reduction in the availability of bandwidth. So we can observe here that as the length increases, broadening or spreading of light pulse increases. That results into maybe errors, intersymbol interference, and that can cause the reduction in the bandwidth. Here we have shown the effect of dispersion on different type of the fibers. Multi-mode step index fiber. Multi-mode step index fiber. This is the input pulse. This is the output spreaded pulse or after dispersion. We can see that the dispersion is maximum. When the dispersion is maximum, bandwidth availability will be minimum. In the case of graded index, this is the case of, as we have seen the profile, parabolic profile. So this is the case of multi-mode graded index. This is the again input pulse. This is the spreaded output pulse, but we can see that the broadening or spreading is less as compared to the multi-mode step index. So basically graded index performs in between. Next, in the case of single mode step index fiber, we can see that this is the input pulse and this is the corresponding output pulse, and this results into minimum dispersion. Broadening or spreading of light pulse is minimum here. So bandwidth availability, single mode is propagating, so bandwidth availability for the mode is maximum. Okay. So basically in any optical fiber, we represent a term known as information carrying capacity. Information carrying capacity of fiber. Information carrying capacity of the fiber is basically a product of bandwidth into length, and this value will be a constant for any type of fiber. Okay, so if we operate a fiber for a lower length, then the bandwidth availability will be more, and if a fiber is operated for a long distance, then the bandwidth availability will be reduced. That is, the bandwidth into length product for any fiber is a constant, and this is termed as the information carrying capacity of the fiber. We can see that the information carrying capacity of the fiber will be depending upon this bandwidth, and bandwidth availability is maximum in the case of single mode step index and minimum in the case of multi-mode step index, and in between in the case of multi-mode graded index. Now the bandwidth or bit rate that is available without ISI can be nearly equal to 1 upon 2 of tau, where this tau is pulse broadening or duration. In the case of Gaussian pulse, we can also represent this as Bt max nearly equal to 0.2 over sigma, where this sigma is RMS pulse broadening or RMS value of spreading. RMS spreading. Okay. Next is types of dispersion. Basically in the optical fiber, two type of dispersion occurs, known as chromatic dispersion or intramodal dispersion. This can be further divided into material dispersion and waveguide dispersion. And second type of dispersion is intramodal dispersion. As clear from the name intramodal, for occurring of this type of dispersion only single mode is required. So single mode can propagate in single mode fiber as well as in the multi-mode fiber. So intramodal dispersion can occur in any type of fiber, any type or all type of fiber. Whereas intramodal dispersion, as clear from the name, it can occur only in the multi-mode fiber. The presence of multi-modes is required in the case of intramodal dispersion. So this can occur only in multi-mode. Okay. So material dispersion is basically intramodal dispersion occurring due to material characteristics, or we can say that whenever we have the condition is d square n1 by d lambda square is non-zero due to the material of the fiber. Here this is n is refractive index of the material, so it is material dispersion. So whenever the intramodal dispersion occurs because of the guidance effect within the fiber, then that is known as the waveguide dispersion. Or we can say that the guidance effect, that will be d square beta divided by d lambda square is non-zero. So because of the guidance effect, it will be waveguide dispersion, or because of the material, it will be material dispersion. And generally this material dispersion is dominating as compared to the waveguide dispersion. So we can say that this chromatic dispersion sigma c is nearly equal to sigma m material dispersion, where sigma m is the RMS pulse broadening due to the material dispersion. Here we have the derivation for the material dispersion. Basically, material dispersion occurs because of the propagation delay difference among the spectral components of a single mode. Basically, this material dispersion occurs due to the finite spectral line width of the optical source. Okay, so the main reason is the finite spectral line width of the source. So different spectral components of the same mode propagates with different velocities. That velocity or that result into the propagation delay difference, that delay is denoted here as group delay, tau g. So the group delay among the spectral components of the same mode are denoted by this. And as we have to calculate the material dispersion, so this is the group delay because of the material of the fiber and after traveling a length of L kilometer. Then the material dispersion can be represented as a function of spectral line width of the source in terms of Taylor series, and these higher terms can be neglected here. So we will have material dispersion nearly equal to sigma lambda d tau m by d lambda, whereas this group delay due to material dispersion can be calculated from previous slide mentioned in that. So we can calculate d tau m by d lambda, this one, and this can be put it into this equation for calculating the RMS pulse broadening due to material dispersion. So after putting, we have sigma m RMS pulse broadening due to material dispersion, sigma lambda L by C and this factor. And now this factor is popularly denoted as capital M. This capital M is known as the material dispersion parameter. Okay, so this is M, material dispersion parameter. So this material dispersion can be represented as sigma M nearly equal to sigma lambda L M. So we can see that material dispersion or intramodal dispersion mainly depends upon this RMS line width of source, length of the fiber or distance covered, and material dispersion parameter. Again, this is the non-zero term. Next is intramodal dispersion. We will see the derivation for the intramodal dispersion. So basically, intramodal dispersion mainly occurs in the multimode fiber, as there is requirement of propagation of multimode in the multimode fiber. So basically, here the intermodal dispersion is caused by the propagation delay difference among the different modes propagating in the multimode fiber. So in the multimode fiber, there can be multi-modes. One may be slow mode, one may be fast mode. So there is a propagation delay difference. That propagation delay difference causes the broadening or spreading of the light pulse, which appears as the intermodal dispersion. So here we can see in the multi-mode step index fiber, we will see that this is the diagram. Here we have considered one axial ray or axial mode, and another mode that we are considering here is extreme meridional ray. Okay. So basically in this we will calculate the propagation delay difference among the axial mode and the extreme meridional ray. This axial mode, as we can see that the distance covered is minimum. So in this case, this will be the fastest mode, and corresponding time will be T minimum. And this extreme meridional ray is slow mode or slowest mode. So if this is slow, then time taken corresponding to this will be T max. So first of all, we will calculate the propagation delay difference among these two modes. So first of all, we will calculate the T minimum. T minimum equal to distance by velocity. So it will be ln1 by c. Now for the case of extreme meridional ray, we will calculate the T max. It will be L by cos theta into C by n1, that is ln1 by c of cos theta. Now from this we can see that theta equal to 90 minus phi c. So it will be cos of 90 minus phi c, that will be sin of phi c. And we know that sin phi c equal to n2 by n1. So we can put here. So we will calculate T max in terms of n1 and n2. We have calculated T minimum. So we can calculate the propagation delay difference among the two modes, fastest mode and the slowest mode, that is T max minus T minimum, given by this. So finally we can, putting the value of delta, we can get the propagation delay difference among the two modes in terms of delta ln1 delta by c. So propagation delay difference among the fastest mode and the slowest mode is ln1 delta by c. We can also represent this propagation delay difference in terms of numerical aperture, because using the formula numerical aperture equal to n1 into 2 delta power 1 by 2. So from here we can calculate the value of delta and put in this in terms of numerical aperture. So that will give this one. Okay. Now for calculating the pulse broadening due to intermodal dispersion, we are considering the input pulse with a unit area and corresponding output pulse. We can check the broadening or spreading of light pulse. So this is the PIT is the input pulse with the unity area with limit minus infinity to plus infinity. Now we have to calculate the pulse broadening due to corresponding to input pulse, that is the propagation delay difference among the two modes. So pulse with unit area using this can be represented as this. If we take the magnitude as this and rectangular pulse and this is the duration, we can represent this as. Now the intermodal dispersion RMS value can be represented in terms of angular moments. Okay, temporal moments M1 and M2, and this M1 is generally neglected here. So we have sigma S2 square nearly equal to M2, where this is the second temporal moment T square PIT dt. And now this PIT can be represented in terms of that rectangular pulse. Okay, so we can put here T square Pi will be magnitude this one dt, and this limit minus infinity will be replaced by this one, and this plus limit will be replaced by this one. So in this way we can compute the intermodal dispersion, RMS value for the intermodal dispersion. So by solving this, we can calculate the intermodal dispersion in terms of propagation delay difference delta Ts. Now putting the value of this delta Ts maybe in terms of delta that we have earlier calculated ln1 delta by C. And similar way we can also represent that in terms of numerical aperture. Okay, as we have calculated for the step index fiber, in the similar way we can calculate the intermodal dispersion RMS value of intermodal dispersion for the graded index fiber in terms of delta as ln1 delta square 20 under root 3 C. So that's all for this lecture. Thank you everyone. We have used references here. So these are the two references: Optical Fiber Communications Principle and Practice by John Senior, and we can also refer the AKGEC for the references. So that's all for this lecture. Jai Hind.